Okay, let's take a look at a typical example. I thought maybe number 14 from the homework would be a good one to look at. So the instructions here say use the method of cylindrical shells, and we'll rotate around the x-axis. They want you to sketch the region and a typical shell. Notice for number 14, one of these functions is not solved for x or y. The other one's solved for x rather than y. This is where it's really nice to use an online grapher instead of your TI-84. So I guess the coronavirus has some benefits for us as calculus students. So the graph looks something like this, and you'll notice I use Desmos. I could just type in x plus y equals 3, and I could just type the two functions in directly as they were stated in the problem, and there's the graph of the two things. So they want us to rotate this around the x-axis, and they want us to rotate it around the x-axis using the method of cylindrical shells, which is actually good. If we tried to use disk washer, so let me just draw what disk washer would look like first of all. If we did disk washer, so here's our axis of rotation, is the x-axis. If we try to do disk washer, we'd have to run a rectangle perpendicular to the axis of rotation, which gives us dx, which initially you're sort of happy about until you realize this thing's not solved for y. You could do it, but it wouldn't be that much fun. But the other difficulty is when you're looking at inner and outer radius here. Inner radius goes to the line, outer radius goes to the parabola, that's fine. But then over here, for this other part of the chunk, inner radius goes to part of the parabola, outer radius goes to the other part of the parabola. You would have to set up two different integrals. They'd have to change right there. So overall, it could be done with the disk washer method, but wouldn't be a whole lot of fun. And fortunately for us, the instructions are just to do it with the cylindrical shell method. So let's do it with cylindrical shells instead. So doing it with cylindrical shell, our axis of rotation is still the x-axis. But now cylindrical shell, when you rotate a rectangle that's parallel to the axis of rotation, you get a cylindrical shell. That means that we'll be dealing with dy, and it does mean that no matter where within this shape, the shape that we're rotating is the enclosure of the two curves. So no matter where within that shape you are, up high or down low, the typical rectangle always starts at the line and ends at the parabola. So we're not going to have to set up two separate integrals. Okay, so let's see if we can set this thing up. Since we're doing it in dy, I'll figure out my y limits of integration from the lowest to the highest, and I am integrating from 0 to 3. And keep in mind when we do this, we are doing 2 pi 2 pi radius. Radius this time is this distance right here. That distance right there is just y. And fortunately our variable is y. We don't need a function that describes y. We're just integrating with respect to y, so we can just put a y in there. Say that distance to the radius from the axis of rotation to the typical rectangle is just y. And the thickness of one of our shells is the dy. So we've got sort of the length and the depth, and we just need the height of one of these rectangles. So we just need this distance right here. And that height is going to be the difference between the green line and the blue line. So the green line is given by 4 minus parentheses y minus 1 squared. And the blue line, and keep in mind we want this in terms of y. So we'll need to solve this this blue line for x. So let's say x is 3 minus y. So there's our whole setup. We've got the radius right here of one of our cylindrical shells. And so 2 pi radius, and then the height of one of those shells is the difference between the two functions, which we have here, and the thickness of one of the shells is the dy. Okay, so this needs a little bit of cleanup to integrate. Let's see, I'm going to pull the 2 pi out front because that's just a constant multiple. And for the moment, I'm just going to leave this multiplied y right there. I'm just going to say this is 4 minus, and I do have to do a little multiplication here to multiply that out. So that's going to be y squared minus 2y plus 1. Keep in mind that's still inside the parentheses because it's still all subtracted. And then I'll distribute this minus sign here. So it'll be minus 3 plus y dy on the end. So we get the integral from 0 to 3. And now I'm going to distribute the y. And I'll try to distribute the minus sign at the same time. So hopefully we won't screw this up. Here we go. So we'll get 4y. And then we'll get minus y cubed. We'll get plus, because we're distributing that minus sign, plus 2, and we're also distributing the y, so 2y squared. And we'll distribute the minus sign, so minus 1 times y is minus y minus 3 plus y. And now, finally, we're getting to the sort of integral that seems like it's not going to be too bad. Let's see if I can cancel anything here. Combine like terms. I've got a minus y and a plus y. I think that's it. So we're looking at minus y cubed plus 2y squared. Plus 4y minus 3. So it's got several terms, but the integral is not bad. Let's see, we've got 2 pi times minus 1/4 y to the 4th plus 2/3 y cubed plus 2y squared minus 3y, evaluated from 0 to 3. Plugging 0 into all of that is just going to give me zeros, which is nice. So my final answer is going to be 2 pi times what I get from plugging in 3. So 3 to the 4th is 81. So minus 81/4 plus, let's see, 3 cubed is 27 times 2 is 54/3. Let's see, what am I on this term right now? So plugging in 3 squared is 9 times 2 is 18. And minus 3 times 3, so minus 9. And you could combine all 4 of these numbers into one number by getting some common denominators, and I'm going to be super lazy right here and not do that part because I know you could do that, but that's the final answer on that problem. So we'll look at least one more example in the next video.